so two things about law of sines and law of cosines. They work for any triangle. So this is important because SOHCAHTOA only works for right triangles, all right? So if you are given a triangle that is not a right triangle, do not try to do Pythagorean theorem or SOHCAHTOA. You are wasting your time and you're going to get the wrong answer. It only works for right triangles. Those two things only work for right triangles. However, from those, we can get other theorems that have been proven, all right? And so the first one that we talk about is law of sines. And I will say this book flips them, but it is whatever's easiest to do. So I think last year's book, it had sine of A over A equals sine of B over B equals sine of C over C. That is the same thing. So if you have two equivalent fractions, you can flip them, right? And so if you remember from last year, it was written like this, but that is the same thing. So really, I would say write it however is easiest to solve. Meaning if you're solving for sine of B, put your sines on top. If you're solving for a side length, put your side lengths on top, right? Because it's just easier to solve when your variable that you're solving for is in the numerator, all right? But it works either way. This is your law of sines. They give you the whole theorem of how it works. They actually use SOHCAHTOA to set this guy up. They draw the altitude. So the altitude, remember, is from the vertex perpendicular to the opposite side. And then they use SOHCAHTOA to solve it. So they'll say like the sine of A is going to be opposite over hypotenuse. The sine of C is going to be opposite, which would be H over hypotenuse A. And so then you get setting them equal and solving for the same variable, which they solve for H is what they solve for when they do this. And then they come up with law of sines. And so you can look at the theorem of how they came up with it. If I were you, I would just memorize this guy. It's really easy to memorize, all right? And so this is what you're going to use if you do not have a right triangle, but you have an angle and a side opposite. Angle and a side opposite. Then you will be able to use law of sines. All right. So the first example here says solving the triangle. Now, solving the triangle means that they want you to give them every angle and every side length. That's what solve a triangle means, every angle and every side length. They've given you two of the three angles, 34 degrees, 76 degrees. We have a triangle. If we have two of the angles, how do we find the third one? They all add up to 180. So I'm going to say, well, to find my third angle, which would be angle C, that's going to be 180 minus 34 minus 76. That's going to be a 70-degree angle. And so it may help to draw a triangle. That's fine. You can draw a triangle. These are all going to be acute, right? And so I'm going to then label my triangle. I'm going to say triangle A, B, and C. When I am solving a triangle, I will list angle A, angle B, angle C, right? And I'll give those measurements. Well, it helps to write the right angle. And I will say side length A, side length B, and side length C, so that I make sure I have filled in every piece of the triangle. That is how you solve a triangle. They gave me two of the angle measures, so I'm going to go ahead and fill those in. And then I solved for the third one. So I know all of my angle measures. They gave me one side length, so I'm going to go ahead and write that side length. All right? Drawing a triangle will probably help you. So if you draw the triangle, you may want to go ahead and say if that's the A side that I drew, it doesn't matter how you draw it, by the way. Doesn't matter. This is just for your visual to help you solve it. The lowercase a is going to be the guy opposite this. So that's going to be lowercase a. If I have B here, then I have B there. If I have C here, then I have C here. Okay, so that's how you're going to set it up. When it says sine A over A, it means the angle and the side opposite of that angle. So this just gives you a visual. You do not have to draw it if you do not want to, but it gives you a visual of what's going on. All right. In order to use law of sines, you have to have at least an angle and the side opposite. If not, you're going to have to use the other guy that we're going to talk about, which is law of cosines. Okay. So I have an angle and a side opposite, so I can use law of sines here. And then I'm just going to set it up in my law of sines. I'm going to say, now I'm solving for a side, so I'm going to put the sides on top, okay? So I'm going to say side A, which is 9 centimeters, over the sine of A, which is 34 degrees, should equal the side B over the sine of angle B. All right, and that's how I'll solve for the side B. All right, if I want to solve for another side, I'm going to use the one that was given, so I'm not rounding and rounding. All right, and so I'm going to set up the same exact thing to solve for C. I'm going to say side A over the sine of A will also equal the side C over the sine of C. And then I'm just going to multiply and solve, right? Multiply both sides here by the sine of 76. So B is going to equal 9 times the sine of 34 degrees times the sine of 76 degrees. C is going to equal, this is divided by the way, divided by 9 divided by the sine of 34 degrees times the sine of 70 degrees, all right? You can put that all in your calculator. They're rounding to the nearest decimal. So you should solve that B is 15.6 centimeters and C is 15.1 centimeters. Really quickly, this is a time when you want to double check what mode you are in. All right, for this, you're always going to be using degrees, okay? Because we're talking about triangles. Typically, triangles don't use radians. Sometimes they do when you're talking about a word problem or navigation, but for the most part, you're going to use degrees, okay? And so make sure your calculator is in degrees. I typically don't go into my mode. I just do like sine of 30. Sine of 30 is 1/2. I always know that. So I do a quick check on my calculator and do the sine of 30. I'm like, okay, I'm in degrees. All right, if it gives me some crazy decimal other than 0.5, I know I'm in radians, and so then I correct it, all right? But do a quick check of your calculator to make sure that you are in degrees when you do these. And yeah, you do have word problems with these. Johann and Wesley stand 360 feet apart on a level football field to observe the flight of a rocket from opposite sides. If Johann records a 72-degree angle of elevation to the apex of the flight path, and Wesley records an 81-degree angle of elevation, determine the distance from the rocket to each observer and the height of the rocket's flight. All right, so this is a little two-part. I probably would draw a triangle here. So the rocket is going straight up. And actually, I drew it like an isosceles triangle. It's not necessarily like an isosceles triangle. So I'm going to try to do it where it doesn't look like an isosceles triangle. The height is going to be perpendicular, though. The vertex to the ground is what we're talking about for height. And they drew it a little bit different than me, but that's okay. So we'll say this one is 72 degrees, which clearly it is not. And we'll say this one is 81 degrees. As you can see, I'm not exact here because those are not correct as far as angle measure. You do want to say that Johann recorded the angle of elevation to the apex at 72 degrees. Wesley recorded it at 81 degrees. Okay. The only side we know is how far apart they are. So we actually know this side length here because we know how far apart they're standing. All right. They want to know the distance to the two heights. All right. And so this is my first distance. This is my second distance. All right. You can label them W and J. I will say that with this type of word problem is a little confusing because if I were to do the opposite side here, that's actually the distance Johann is going to be from the rocket, right? And if I put a J here, that's actually the distance that Wesley is from the rocket. So the reason I didn't use J and W here is because I would actually label it wrong probably when I got to my final answer because I would think, oh, W means how far away Wesley is, and it's actually vice versa in this one if you understand what I'm saying. All right, I do need to know that third angle, just like in the one they gave me. So I do need to do the 180 minus the 81 minus the 72 to get that angle up there. I am again solving for side lengths, so I'm still going to put my side lengths at the top. All right. So I would say then the distance 1 here, or Johann's, across from Johann, over that 72 degrees will equal the 360 over the sine of the 27 degrees. All right. And then I'm going to solve for that distance. So I have the 360 divided by the sine of 27 times the sine of 72. I will get approximately 754 feet here. So this is approximately 754 feet. Okay. And I'll do the same thing for distance 2. Distance 2 over the sine of 81 equals that same 360 over the sine of 27. When I multiply across, I'm going to get approximately 783 feet. So that's how far the two are apart. So that means Wesley is 754 feet from the apex of the rocket. Johann is approximately 783 feet from the apex of the rocket. All right, which makes sense, by the way, if you think about logics, right? If he has to look further up, it's closer to him, his range of view. The height of it's going to be the same no matter what, right? If you're having to look further away, then the point's farther away from you. So it would make sense that the one that has the higher angle of elevation is actually closer to the rocket because it's more above him than it is the other guy. Okay, so you can use your logic a little bit there to help you see if you did it correctly. So they technically are asking for this right there. You can use either one of these, but you are going to now use SOHCAHTOA, all right? You're going to say then, you can't use this because you do not know how far, like, you don't know where they shot the rocket off, so you don't know that distance, but you do know this one and you do know an angle. So you can actually use either one of those to use opposite over hypotenuse, the sine, okay? So you could say the sine of 72 equals the height over 783, or you could say the sine of 81 equals the height over 754. Either one of those will give you your answer. And so, all right, so approximately 745 is how high the rocket went. Approximately 745. ambiguous cases. By the way, if one of your angles is obtuse, that's the only one that's obtuse. Okay, you can't have two angles in a triangle that are obtuse, right? Because they have to all add up to 180, and we're above 180. So you can automatically assume that. You have these ambiguous cases where like, well, it could be this or could be this. What actually happens with an ambiguous case is you get something outside of your sine domain from -1 to +1, and cosine domain, -1 to +1. And so when you do these, if you get an error, then you have one that cannot be, they've given you ones that would not work for a triangle is what they've done, okay? Not that I'm going to give you any of those, but just keep that in mind. There are ambiguous cases that then when you work them out, which is what they work out in example 3, that you end up with an ambiguous case that gives you a sign that's outside the -1 to 1 for your domain. All right. They do get law of cosines from the Pythagorean theorem. I'm not going to make you memorize the proof of the law of cosines. But it is from the Pythagorean theorem. They've done, again, the altitude, and they've done a squared plus b squared equals c squared. I will say they labeled the a across from the a angle, but that's actually your hypotenuse here. So don't get, this is the hypotenuse. This is these are your two legs. So leg squared plus leg squared equals hypotenuse squared. And then they just solved back into it to get this little guy here. Law of cosines is one you probably then just want to memorize. You're probably not going to be able to generate that on your own. So you do want to memorize it. It's not hard. It looks hard. They give you 3 different ones, but it really just depends on what angle you have. This is when you have one angle and 2 sides, and the sides are not opposite the angle that you have. All right. So if you have 2 angles and a side, you can always use law of sines because angles add up to 180. But if you only have one angle and the 2 sides that you have, neither of them are opposite that angle, you're going to have to use law of cosines. All right. And so all this is saying is, I have the angle. I do not have the side opposite. Okay. So whatever angle you have, this is what you're going to do. The other 2 angles squared. So the other 2 sides squared plus side squared, minus 2 times those sides, cosine of the angle, okay? All right, so like if I have angle A and I do not have side A, then it would just be b squared plus c squared minus 2bc cosine of A. If I have B and I do not have side B, then I'm going to say a squared plus c squared minus 2ac cosine of B. All right, so you don't really have to memorize the sides. What you do need to know is the 2 sides that I have, I'm going to square those and add them, minus 2 times the side lengths, cosine of the angle that I have. All right, cosine of the angle. So you'll notice the guy out here and the angle are always the same, and these are the other 2. The ones in here are the other 2 sides, okay? All right, so that's all you have to remember. You don't have to try to remember all 3 of these formulas. It's because it might not necessarily be labeled A, B, and C, right? It may be any variables. Let's look at using it first. The first one is just solving. All right, how do I know that I need to use the law of cosines? Well, they gave me angle A, and they gave me side length B and C. And they want me to solve for all of these, okay? And so I'm going to solve for the side that's opposite the angle. All right. And so again, I'm going to set up my 3 angles, angle A, angle B, angle C. I'm going to set up my 3 side lengths, A, B, and C. And then I'm going to fill in what they've given me. They've given me angle A, side length B, and side length C. All right. So my first step is going to be to solve for side length A, because once I have side length A, what can I use? I can use the law of sines, right? Which is an easier one to use. And then once I have 2 of my angles, all I have to use is the fact that they add up to 180, and I have solved the entire triangle, okay? So I'm going to use the side length that's opposite of A. I'm going to say A squared equals B squared. Well, B is 12. So my 2 side lengths that I know, minus 2 times those 2 side lengths, cosine of the angle that I know. All right. And I am going to not try to do that in my head. Okay? So once I set it up, feel free to use your calculator. Yes, 12 squared is 144. 9 squared is 81. You can do 2 times 9 times 12, right? But you can't do cosine of 23. And you're really going to get a decimal here anyway. All right, so if you plug all of this into your calculator, make sure, okay, in your calculator, if it's squares, some of your calculators will stay in the exponent position. Make sure you drop out of the exponent position before you add. So just pay attention to your entry when you do this, all right? When you put that into your calculator, you should get that a squared equals approximately 26.17. When you take the square root of that, a is approximately 5.1. Why did I not do positive or negative 5.1? They actually told us we were talking about a triangle here, which means that my side length has to be positive. Okay. So if we were doing vectors, by the way, direction might change whether that's positive or negative. Just keep that in mind if we were doing vectors. Okay. But we're not talking about direction here. We're talking about length. All right. So now I know this side length. I am actually going to move to law of sines at this point. All right. So if I want to solve for angle B, now remember, if I'm solving for my angles, I'm going to put those on top. So if I need to know the angle B, then I would say, well, the sine of B over the side length of B should equal the sine of A over the side length of A. All right. How do I solve for the sine of B? Well, I multiply both sides by that 12. Sine of B equals the sine of 23 times 12 over 5.1. What am I actually solving for here? An angle or a side? If I am solving for an angle, what in your calculator do you have to use? Your inverse. So in your calculator, B is going to equal the inverse sine of all of this. Okay, so in your calculator, you should be able to do inverse sine, open parentheses, sine of 23, make sure you close that parentheses there, that's 23, times 12 divided by 5.1. All right, you should be able to do all of that into your calculator. You should get approximately 113.6. So way back in geometry when we ordered triangles, all right, your longest side length corresponded to your largest angle, correct? Yes. All right, and so when you don't know whether or not you have an obtuse, which by the way, bare minimum you could have maybe a 90. If you did 90 in 23, you would have what 113, right? And then you have, so you either have an obtuse or you have like, you know, a 90 degree and a smaller one, because you're going to have close to it if not. So when you don't know, do your smaller one, all right? Because it actually gave you the reference angle is what it did. So we'll do the smaller one and then we'll know. So I'm going to delete this. We will do the smaller of the two because we don't know. And we'll solve for C first. And then we're going to back into B using 180. So we're going to do C first because it's the smaller and we don't know if we have an obtuse angle at this point. So we're going to say the sine of C, which is what we're solving for, over C equals the sine of A over 5.1. So remember, you have to do inverse sine of sine of 23 degrees times 9 over 5.1. You should get that C equals approximately 43.4. They rounded this part of it, and then they plugged that into their calculator. So we didn't, so I'll take the 43.6 because that's probably more accurate than what they did. And then you can back into your B, and you're going to see that B is going to be an angle that is larger than 90. It's going to be obtuse. So now you can, for this guy, you can say 180 minus the 23 minus the 43.6. You get 113. Y'all will get 0.4 because y'all rounded differently. Yeah, you can totally check these. They should work for law of sines, right? So sine of A over A should equal sine of B over B should equal sine of C over C. Keep in mind you rounded two of those, right? So you may be off by a decimal place or two way out there, but you should be pretty close. All right, they should all equal the same. You can check these with law of sine. I love this because this shows you, hey, by the way, they use trig to do triangulation when someone calls from a cell phone, right? I actually know a good friend of my mother's who they found him by doing this, by this triangulation, right? And so they ping a cell phone, and they have to have at least 3 towers to actually triangulate it. This is why. This is why 3 towers have to ping off of a cell phone, because they're using triangulation to do it. They found the distance between the three towers, 5.6, 2.7, and 4. All right. And they wanted to know the possible headings. You can use law of cosines here. You'll notice you have no angle, right? But if you have 3 sides, you can use law of cosines, right? This is what's important in this example, because you can say a squared equals b squared plus c squared minus 2ac sine of A, 2bc sine of A. And you can back into your angle, right? If you have 3 sides, you can plug in your 3 sides and you can solve for what's missing, right? You would square this, subtract your bc squared over, divide by your negative 2bc, and then do your inverse sine, okay? How does this help them? Well, because then there's only 2 locations that could be happening here, right? It could be either a positive or a negative movement from those locations. And so it narrows it down to 2 different locations, 2 different bearings from that. And they're able to narrow it down to 2 locations at this point. And we're not going to do when they have a 4th, but if they have 3, they can at least triangulate it and get it down to 2 locations, which is what, and they're using law of cosines here. So you don't have to have an angle to do law of cosines. You can have 3 sides and you can solve back into it using your inverse cosine to do it. And that should be cosine, by the way. Ignore my quickly writing. This guy right here should be cosine of A. Area formulas. There are two area formulas we're going to talk about. They do come from these laws. The first area is you have two sides and a side opposite, all right? You're going to say 1/2 the two sides that you have, sine of the angle. So 1/2 AB sine of C, 1/2 BC sine of A, 1/2 AC sine of B. So you really need all three sides, which means you may have to solve for either one of the angles or one of the sides, because you really need to have the two sides and the angle that's not opposite one of your sides, okay? So in this case, I have this guy, which means I really either need another angle or another side, whichever one. And then you can solve for that side or that angle, and you can then use the other one. So if I have these two sides, then I really need this angle, right? Or if I have this angle, I need these two sides to use this formula, because you'll notice two sides and the third angle, not opposite those sides. So you have to solve one way or the other. They actually solved for the angle R. Why did they solve for angle R? That was not how I would do this. I would solve for angle P. So that's just me. So let's solve for this angle. All right, so if I have him, then I need this guy to use this thing. So I am going to solve for an angle, and then we'll just subtract it out. That's what we'll do. That's why they did that. So we'll say sine of 56 over 10 equals sine of R. They like to make this difficult, over 9. In your calculators, sine -1 to solve for R is going to be sine of 56 times 9 over 10. So R is going to be approximately 48.3. That's why they did this. 180 minus 56 minus 48.3 gives me 75.7. All right, so we just use law of sines to get that guy right there. If I have the angle and the two sides that make up the angle, I can find the area using this. So I need to find the area of this triangle. It's going to be 1/2 the two sides that make up the angle. 9 times 10 times the sine of the angle. This is going to be the same thing as if I had the height. So if I had this height, I would do 1/2 base times height. I don't. So I can use this formula. 1/2 the two sides times the angle in between the two sides. Has to be side, angle, side to use this guy, okay? So one way or the other, I have to have side, angle, side. I have to be able to do that to be able to use this one. Side, angle, side to use this formula. Side, angle, side, okay? If you don't have side, angle, side, you're going to have to use one of your laws to get it, all right? And then you just 1/2 your two sides, your sine of your angle, all right? That's all you do. When you plug this guy in, what do we get? We get approximately 43.6. It is squared because it is an area. All right, so it is squared. Your units are squared there. All right, there's one other area formula. All right, Heron's formula. Heron's formula is based off of actually the sine formula that we just did. It's this crazy proof that I'm also not going to make you memorize. It is used the semi-perimeter. This is when you have side, side, side. So I don't have any of my angles, but I have 3 of my sides. If it were a right triangle, we could do 1/2 base times height. We're talking about non-right triangles, right? The semi-perimeter is 1/2 the perimeter, hence the term semi-perimeter, okay? And so to find your perimeter, like for this one, we would say, if I need to find the semi-perimeter, that's just going to be 1/2 my perimeter. So my perimeter is 820 plus 638 plus 1100, okay? That is my semi-perimeter. So when you look at this formula, that's what that S stands for, okay? Weird formula, but it works. It's Heron's formula. It works every time for finding the area. So I'm going to take that guy, that semi-perimeter that I find for this, which by the way is 1,279. When I add those up and divide by 2, that's my semi-perimeter. So I'm going to use him, plug him in. And then I'm just going to multiply by what happens when I subtract each side from that semi-perimeter that I just found. So I would take 1,279 minus my first side times 1,279 minus my second side times 1,279 minus my third side. It's really just a memorization. Find half of your perimeter, your semi-perimeter, and then in the root, you're going to multiply that by the subtraction of each of the sides, okay, from that semi-perimeter. Again, you have a calculator for a reason, all right? It ends up being, this is all in feet, it ends up being approximately 259,536 square feet. It wants it in acres. Not that you know this, but 43,560 square feet in an acre. How many people know that conversion? All right. Anyway, this would be your area, by the way. I'm not going to make you do a conversion from feet squared to acres on your test, I promise. But if they wanted it in acres, they would probably give you that conversion anyway. But that's what your area would be. So just half your perimeter, and then you multiply that times the difference between each of those sides in that half perimeter and take the square root, okay? That's what your Heron's formula is. So obviously side angle side's easier, I think, 1/2 AB sine of C. But Heron's formula is not hard. It's just a lot of numbers, pretty much. All right?